So section 2.2 is called More Graphs and Displays. Okay, starts off with graphing quantitative data sets. You guys already talked about quantitative versus quantitative, right? I just said exactly the same thing. You know what I'm talking about, right? Qualitative and quantitative. Sorry about that. Okay, I'm trying so hard to make sure my vocabulary is good, and I'm saying exactly the same word. Okay, sorry about that. So I'm going to talk to you a little bit about some different kinds of graphing that you might see or that you will see. Okay, so the first kind of quantitative data set is called a stem and leaf plot. Have you guys ever heard of a stem and leaf plot before? Have you ever made a stem and leaf plot before? Okay, so let me make sure you understand what's going on in a stem and leaf plot. Okay, first of all, in a stem and leaf plot, surprisingly, you have a stem and a leaf. Okay, I know that's shocking, all right? But what you need to understand is that you should have as many leaves as there are entries, and the leaves should be single digits. Okay? You'll understand that. I think if you don't now, you will in a second when I show you a stem and leaf plot. Okay? It's very similar to a histogram, but it still contains all the original data. It's just not a bar about the histogram. It still contains all, like a histogram, it still contains all the original data. Okay? It also provides an easy way to sort data. All right? So if this is the data set that I have given you, or that the book has given you, or your boss has given you, and you have to arrange this so it makes more sense so that you can see something more clearly, you're going to decide what is the stem and what is the leaf. Well, in almost all of these, every single one of these numbers in the data set are 3 digits, right? With one exception right here, but that's not going to be too big of a deal. But if they're all 3 digits, knowing that the leaves have to be single digits, you know your leaf is going to be 1 digit. So how many digits is your stem going to be? 2 in all but that one piece of data, right? Okay. So the lowest number is 78. I think that's pretty obvious because everything else is 3 digits, right? So we're going to start off with, let me see if I can slide this up real quick. We're going to start off with 7 and 8. 7 is my stem and 8 is my leaf. Okay? Well, if 7 is my first stem, guess what my next stem is? 8, and guess what my stem is after that? 9, and then what? 10, right? 10 is my next stem, but I have to have the leaves that go. Up until now, nothing else is 2 digits, so nothing else has happened in my stem and leaf plot. Okay? So what has to happen next on my stem and leaf is I have to figure out all the numbers up here that have a 10 as their first 2 digits. Well, there's 1. There's 1. There's 1, there's 1, there's 1, and I think that was it, right? So I had a 5, an 8, a 9, a 9, and a 9, right? So I had 105, 108, 109, 109, 109. Do you see how those are represented on the stem and leaf plot? I know, it's okay, it's okay. Okay. So then I have my whole stem and leaf plot set up. So you see how the 105, 108, 999, like that 109, 109, 109, I mean. Does that make sense now? Now, something that's really important to have in a stem and leaf plot is a key. Okay? Because this value right here, this number could actually be representing 7.8. Does that make sense? But I know that it's representing 78 because of the key that it's set up. I know that the leaf is in the ones spot, and the stem is in the tens and the hundreds spot. Does that make sense? Okay? So, do you see how all of these data points are still represented? You guys remember what a histogram is, right? It's kind of like a bar graph that gives you a value between 105 and 109. Well, we'd just have a bar graph there, and you wouldn't know that it was 105, 108, 109, 109, 109. So this gives you all the data that was there. Gives you every data point still. Okay? There's also an alternate way to set up a stem and leaf plot. And here it is. Here's an example of it right now. This is just one of the examples that you could set up. Another way you could set up a stem and leaf plot. What do you notice about the stems? They all repeat, right? There's 2 7s, 2 8s, 2 9s, and so on. can't really tell what's going on up here, but if you look down here, look at this. Look at that 11 and then look at that 11. What did they do with the leaves? They separated them, didn't they? Okay. This 10 represents the 100 and something, right? And then the leaves go from 0 to 4. And then these leaves go from 5 to 9. These leaves go from 0 to 4, and the next ones go from 5 to 9, and so on. Does that make sense? Just an alternate way to set it up. Gives you a little bit more view of the data. Just a different view. Okay? This says you obtain a more detailed picture of the data. Okay. All right. Any questions on a stem and leaf plot? So something that's interesting is that we could also have a dot plot. Okay? Like a stem and leaf plot, a dot plot allows you to see how data are distributed to determine specific data entries and to identify unusual data entries. We didn't really talk about the unusual data entry in the stem and leaf plot, but I'll go back and talk to you about it real quick. But do you see an unusual data entry in this dot plot? Where is it? Yeah, it's all by itself, right? See how far it is away from all these? Are these two really by themselves? I mean, they're kind of by themselves and not really. They're still kind of close to the rest of these, but this is way far off by itself. Okay? It's actually called an outlier, and we'll talk about that in just a second, but I wanted you to notice that real quick. Okay? Because if we look back at the stem and leaf plot, I wanted you to see that you can also see the outlier there as well. See how these whole two lines are blank, and then there's one, right? Okay? But here's the cool part about a dot plot to me. Okay? Here's the dot plot that they have. But what if I took a stem and leaf plot and just turned it sideways? Isn't that kind of like a dot plot also? Underneath the 120 of this many, right? It's not exactly, I know that, and you know that, but it's kind of, isn't it? It's very similar, okay? It's similar in how it's representing every point that you're given, okay, on a horizontal axis. All right, any questions about a dot plot? Not talking about a whole lot because we did some of those last year. Okay. The next kind of graph that we want to talk about talks about qualitative data sets. When we're talking about qualitative data sets, can we see all the individual entries? Not anymore. Okay. A pie chart is one of those possibilities, and you guys know that it's a circle that's divided into sectors that represent categories. Okay. The area of each sector is proportional to the frequency of each category. Kind of a little bit of the definition going on right there. Okay. Most of the time you're going to have to be interpreting pie charts or creating them with technology. Most of the time you don't have to make pie charts anymore. Okay. But I think if I ask you to make a pie chart that you could, because you guys were all pretty relatively good at geometry. And that's what you have to be good at, right? You have to be able to figure out the percentage or the proportion of the circle that contains that much to be able to figure out the angle that you need to measure to represent, in this case, like a master's degree, 74 degrees. Does that make sense? Okay. Another kind of qualitative data is a Pareto chart. Okay. Guys, to be honest, I've never heard of this before. Probably should have, but now I do. Now I know. Okay? A Pareto chart is a vertical bar graph. In fact, when I looked at it, I even thought it was a bar graph. Okay? But it is a kind of bar graph. It's a vertical bar graph. The difference is that the height of each bar represents the frequency or relative frequency, kind of like a pie chart. However, it differs from a bar graph in the fact that they're positioned in decreasing height. Okay? Starting with the tallest. This positioning does help highlight the important data and is frequently used in business. So those of you who are going into business might see some Pareto charts. Well, when you're at work. Okay? And when you see one, I want you to think, I'm doing math. I should call Miss Kingston. And then you should call me and tell me you're doing math. Fair? Okay, good. So here's an example of a Pareto chart. What can we tell? What's the most obvious thing that stands out in this Pareto chart? Hopefully employee theft. because it's the biggest, right? It's the first thing we see. It's the biggest. It's the one that we notice the most often. That's why it's set up this way. Okay? Any questions about a Pareto chart? If you make one, what do you have to make sure to kind of order to put it in? Biggest to smallest, right? Okay? Now, I'm going to talk about these for approximately 3.4 seconds because they're scatter plots. Okay, done, right? We don't have to talk about scatter plots hardly at all because we definitely did those in Algebra 2, didn't we? Okay? In Algebra 2 and in the dual credit Algebra 2, we talked about scatter plots, all right? So they come up in statistics. They're called paired data sets. We use a scatter plot to represent them, and it shows a relationship between two quantitative variables. Okay? All right. Then there's a time series. Sometimes they're called timelines. You've seen these before. Yeah? Time series or a time series chart. It's a data set that's composed of quantitative entries taken at regular intervals over a period of time. Okay? So like in this particular chart right here, it's taken every year. Okay? So both subscribers and average bill. So it's taken every year so that we're able to graph it on a time chart or a time series. Does that make sense? Yes? Okay. Then that's 2.2 because here's all the questions that you have at the end of the section. Okay? Any questions on how to read any of these graphs, how to create any of these graphs, anything like that? You good? Okay. Section 2.3 is measures of central tendency. Okay, let me try that again. Section 2.3 is measures of central tendency. Yeah! Guys, you already know how to do this, don't you? This is mean, median, and mode. How long have you been doing mean, median, and mode? 5th grade, 6th grade, something like that. Now, I promise you none of it has ever looked like this, so I need to walk you through some of these formulas that they're going to ask you to do to explain to you that you do know what it is. Okay? So, first of all, let's talk about measures of central tendency. These are the 3 most commonly used, mean, median, mode. We also, in high school, talk about range sometimes as a measure of central tendency, but in statistics, we're mostly talking about mean, median, and mode. Okay? The mean of a data set is the sum of the data entries divided by the number of entries. Now, when I read that, most of you guys just went, duh. You know that, right? But here's the deal. You also know this. You just haven't seen these symbols before. Okay? This symbol kind of looks like a backwards U. It's not. It's called a mu. It's a Greek letter for mu. This is how you find the population mean. We spent last section or the section before that talking about the difference between population and sample, right? Okay? There's 2 different formulas for them, but just wait for a second, okay? To find the population mean, we use the Greek letter mu. And to find the population mean, we take the sum of all the values, right? And divide it by the number in the population, a capital N. But guys, look, to find the sample of the sample mean, not just the population mean, but the sample mean, we're going to use X bar to represent a sample mean, and we're going to take the sum of all the entries and divide it by the number of entries there were. Don't you already know how to do that? Guys, that's all that is the mean. Okay? It's just set up in symbols that you may or may not be familiar with or comfortable with yet. Okay? But remember, all this is saying is add up all the things that are there and divide by however many there are. You may or may not think it's important to differentiate between a capital N and a lowercase n. Let me tell you right now that it's important. That was one of the things that I used to get in trouble for when I was taking my college classes when I first started doing that. Because if it was an N, I would just write an N. And my professor would be like, it's a capital N. I'm like, why does it matter? And he's like, it does. It matters. Yes, sir. Yes, sir. It matters. I'll take care of that. Okay, so capital N's and lowercase n's, capital different letters, A's, lowercase a's, things like that can make a difference and mean something different in math. So we're going to be careful with our with how we write our things out, okay, our formulas. All right. So population mean, we use a mu, and sample mean, we use an X bar. You okay with that? Yes. Okay. So here's a bunch of examples about how to find mean. Do I need to do that for you? Okay. So let's talk about what's next. Median. Woohoo! The median is what? The middle when you line them up, right? Does it have to be least to greatest or greatest to least? Yeah, that's a trick question, right? The answer is yes. It has to be one of those two. Okay? A lot of times we do least to greatest, but it could be greatest to least as long as we're finding the middle. That's what we're finding. Now, you remember this, but I'm just going to remind you because we're talking about it. Okay? When the data set has an odd number of entries, it's the actual middle one. Okay? But if it has an even number of entries, there's going to be 2 ones in the middle, and we find the mean of those 2 data entries to find the actual median of the data. You remember that? Okay. Here's some examples on median. Do I need to do any of those? No? Okay. Last but not least, mode. Woo! You guys aren't as excited about mode as I am. It's okay. It's the data entry that occurs the most often. It occurs with the greatest frequency. Okay? It happens the most often. You are allowed to have one mode, more than one mode, or no mode. Guys, if you have more than one mode, well, specifically 2. If you have 2 modes, it's called bimodal. That seems a little obvious, but I'm just telling you because it's highlighted. Okay? It's in bold, so I'm telling you that. Okay? Any questions on mode? All right. Here comes the fun stuff. Remember I told you earlier we talk about outliers? It's time. The mean is a very reliable measure of central tendency because it takes every data entry into account to get its value. But you need to understand that the mean is the one that could be the most greatly affected when there's an outlier. Okay? It can be greatly affected when it has an outlier. So here's a definition for you. An outlier is a data entry that is far removed from the other entries in the data. Later on we'll talk about a formal way of figuring out what those outliers are, but right now we're just saying it's kind of far away from everything else. Outliers can create gaps in the distribution of the points. Okay? You saw that earlier when we talked about that the dot plot as well as there's the dot plot. You can see that outlier way far away from everything else. And even when we did a stem and leaf plot, it's kind of way far away from everything else. Does that make sense? Okay. Comparing the mean, median, mode. If you take the mean, median, and mode of a set of data, are they all 3 always the same? No. And is that okay? Yes, it is. Okay. You could get this for the mean, and this for the median, and this for the mode. Okay? In this different set of data, the mean takes every entry into account, but again, it's influenced by an outlier of 65. Okay? Here was the set of data that they were using. Can you tell that might really take into account or change the mean when we have a 65 away from all this other stuff? Excuse me. The median is usually not affected very much by an outlier. And the mode, unless it happens the most often, in this case, you wonder why it's called an outlier. If it's happening a whole lot, it's not really affected either. Okay, but in this particular case, the frequency, the one that's happening the most, is 20. Does that really make sense in this set of data as an average? Not really, because it's the lowest one. It's there every time, right? Okay, so that's just talking about the interpretation of the different kinds of measures of central tendency. All right. Here is what you guys I thought would be most interested in. Okay, weighted mean and mean of grouped data. Now you've done all this before, whether or not you called it weighted mean. Okay, because here's an example right here. If you know what your test mean is, and you know what your midterm grade was, and you know your final exam grade, and you know your computer lab grade, and you know your homework grade, do you just add those up and divide by 5? Not unless I told you everything was 20% of your grade, right? But this is making it very clear that it's not. Your test mean is 50% of your average. and your homework mean is, or your homework grade is only 5% of your average. So if we just added these up and divided by however many, that wouldn't be a weighted mean, that would just be a mean, wouldn't it? But we want to weight things. Some of these things are more important to teachers or professors than other things. So we take the score times the weight. Score times the weight. So in this case, x times w, which is evident in this formula right up here. Okay? X times w, and I add all those up to get what the mean is and divide it by the weight, the sum, which in this case is just 1, so it's just the sum of all the entries times their weight. Now, sometimes this column, the weight might end up being 2 or 3 or 4, so I would have to divide my eventual this mean right here, this sum right here by that number. But a lot of times, especially if we're talking about grades, we want to make this a total of 100%. Okay, so that's going to end up being a 1. But in other situations that's not talking about grades, this may be a different number right here, so you would end up having to divide by that number at the end. Does that make sense? Did you guys have time to copy this formula down in your notes if you wanted it? Should I give you just a second? Yes, ma'am. So x bar equals the sum of x times w over the sum of w. W is the weight of each entry, and each entry is x. Any questions about that? Okay, ready to go on? So the mean of a frequency distribution. Now, you guys just talked about frequency distribution, right? And for whatever reason, I'm having trouble today saying distribution, so I apologize about that. Okay. Do you remember how to find the midpoint of each class? Do you remember how to find the frequency of each class? Then finding the mean of the frequency distribution is not going to be a problem for you. Okay. Here's something that's interesting though. Okay. This is x bar. So what kind of distribution is this talking about? It's talking about a sample, right? Would you know how to find the frequency distribution for a population? What would be different? Capital N, right? The number of a population is lowercase n, so the number of the number of a sample is the lowercase n, so the number of a population should be uppercase n. Look. That's the difference. Population, you're still taking the midpoint and the frequency, the sum of their product, and dividing it by the number of population, or the sum of the products and dividing it by the number of the sample. Do you want to write that down? Do you have that? Okay, good. So here's some guidelines to find the mean of a frequency distribution. Okay. Now, again, this is in your textbook or in your online textbook if you need to refer back to it. But just real quick, we'll go through it real quick. Okay. First of all, you need to find the midpoint of each class. Remembering that finding the midpoint is the lower limit plus the upper limit divided by 2. You're remembering that, yes? You're nodding at me? Okay. Then you're finding the sum of the products of the midpoints and the frequency. So this that you just found, and then times the frequency, and then you're finding the sum of all those. Okay? Then find the sum of the frequencies. Add them up. And then divide. Questions? You okay with that? So here's an example I want to walk through with you real quick. Okay? Finding the mean of a frequency distribution. It tells us right here what the class midpoint is and what the frequency. They've already found for the set of data that they have. Okay, so if we have a class midpoint and we have a frequency, the first thing I do is, I already found the midpoint, so then I find the sum of the products. So I multiply these two to get this. Multiply these two to get this. Multiply these two to get this, and so on. And then what do I do with this column? I add it together, right? So that is my, let me slide this down. That's my sum of my midpoint and my frequency. Yes? Then I divide it by the number that there were, and according to the frequency, there were 50. So I take 2089 and divide it by 50, which in this particular example gives me approximately 41.8. Okay, so for this problem situation, the mean time spent online was approximately 41.8 minutes. Okay, any questions about that example? All right, at least not now, right? Maybe when you get into it, but not now. So let's talk about the shapes of some of the distributions, the possible shapes. Okay, it could be symmetric, it could be uniform or rectangular, or it could have a tail, so it would be skewed either left or right. Okay, so let me show you some examples of those so that you can look at it. Looking at this, can you tell that this would be symmetric distribution, other than the fact that I just covered that up underneath it? Does it look pretty symmetric? Like if I folded it in half, it would be close to being on top of each other? So that's symmetric distribution. Okay, what about this one right here? Hopefully that's obviously a rectangular distribution, right? Or a uniform frequency distribution, because it looks like a rectangle. Yeah? Just being honest with you, I mess these up sometimes if I'm not paying attention. Because to me, this looks like it's skewed to the right, because more of the data is to the right. Right? Except, look what it says. It's skewed to the left. The reason it's skewed to the left is most of the data is to the right, so the skew is to the left. And a lot of times what I do is I look for the tail. Okay? They told me last period they thought this looked like Gru's dog. You know, from Minions. Gru, the bad guy, who's a good guy and then a bad guy. Okay, you know who I'm talking about. Okay, they said this looks like Gru's dog. I don't think I've seen it enough to know for sure if I know if this looks like Gru's dog, but I just agreed with them. Okay, and then later they came and showed me a picture, and I really, really did agree with them because it kind of does look like Gru's dog. Okay, but if you look for the tail, see, do you see what I'm talking about? It has a tail. Okay, it's skewed left because the tail is on the left. Okay. This data then would be skewed to the right because that's where the tail is. A majority of the data is on the left, so it is skewed right. This says the mean will always fall in the direction in which the distribution is skewed. So for instance, when a distribution is skewed left, the mean is to the left. Okay? The mean is to the left of the median. Excuse me, I didn't finish the whole sentence. The mean is to the left of the median. See right here, the median is right here, and the mean is to the left of that. Okay? Right here, this is skewed right, so here's the median, and the mean is to the right of that. That's another way to look at it. Does that make any sense? Some sense? A little sense? Okay, good. The graph, let me show you this study tip right up here real quick. The graph of a symmetric distribution is not always bell-shaped, like this one is. Kind of looks like a bell. Some other possible shapes for the graph of a symmetric distribution are a U, M, or W. Can you see how if it was U-shaped, M-shaped, or W-shaped, that would also be symmetric? Because it looks like itself on the other side. Okay? Just something to think about, all right? But that's it for this section 2.3, because here's the problems at the end of the chapter. Okay? If you have any questions on 2.2 and 2.3, let's talk about them as you work through your problems. We may come together as a group, or I may talk to you individually depending on what's going on in the problem. Are there any questions? You good? Awesome. Have a great day. Peace.